Australia advances large battery technology to reshape power storage and delivery across regions. Iron flow batteries are tested at grid scale by Australian energy companies as a durable, low-cost alternative to lithium systems. These batteries use 2 tanks of liquid electrolyte circulating through a central cell stack to store and release energy. Unlike lithium-ion batteries, they do not degrade quickly, making them suitable for daily charge and discharge cycles over many years. By combining abundant raw materials with flexible energy management, Australia builds energy storage systems to stabilise renewable energy sources like solar and wind across its landscape. Iron flow batteries circulate 2 separate liquid electrolytes through a central reaction cell where energy is stored or released. One electrolyte contains iron in a reduced form, the other contains iron in an oxidized form. These liquids are pumped from external tanks through a membrane that allows ionic exchange without mixing the fluids. During charging, electrical energy converts the chemical state of the iron ions. During discharge, the reaction reverses and electricity flows to the grid. This system separates energy storage from power delivery, offering flexibility in battery design. Iron flow batteries do not store energy in a fixed material. Energy is stored chemically in the electrolyte solutions. The total energy storage depends on the size of the electrolyte tanks, not the electrode surface area. Power output depends on the size and number of reaction cells. Designers can scale energy capacity and output independently. A system stores more energy by expanding the tanks while keeping the same number of cells. Each reaction cell has 2 compartments separated by an ion-selective membrane. Electrodes are on either side of the membrane, and pumps circulate electrolyte fluids past these surfaces. During redox reactions, electrons are released or absorbed depending on charging or discharging. The membrane allows only specific ions to pass, preventing the fluids from mixing. This maintains chemical balance and system efficiency over repeated cycles. Iron suits this process due to its stable oxidation states and low cost. One key strength of iron flow batteries is their durability. Because the chemical reactions occur in liquid rather than solid form, there is very little mechanical stress on the battery components. This reduces wear and tear, allowing the system to last for tens of thousands of cycles without significant degradation. The electrolyte fluids can be reused for years, and the reaction cells require minimal maintenance. Unlike lithium-ion batteries, which degrade with every charge cycle, iron flow batteries retain their capacity and performance over time. This makes them ideal for daily grid operations, where reliability is critical. Thermal management in iron flow batteries is relatively straightforward. The chemical reactions do not generate intense heat, so cooling systems can be simpler and more energy efficient than those required for lithium systems. The liquid electrolyte acts as a natural heat sink, distributing temperature evenly across the system. This eliminates the risk of localized overheating, which can damage components or reduce efficiency. In high-temperature environments like those in parts of Australia, this feature provides a significant operational advantage. The lack of thermal hotspots improves safety and lowers the cost of supporting infrastructure. Safety is an area where iron flow batteries excel. The electrolyte fluids are non-flammable and chemically stable, reducing the risk of fire or explosion. This contrasts with lithium-based systems, which require extensive safety controls due to the risk of thermal runaway. In the event of damage or leaks, iron electrolytes do not release harmful gases or catch fire. This makes the technology well suited for use near residential areas, schools, and public infrastructure. It also simplifies permitting and reduces insurance costs for large-scale energy installations. These features make iron flow systems more acceptable to communities and regulators. Iron flow batteries are monitored and controlled through smart software systems. These control systems manage charge and discharge cycles, track fluid levels, and monitor the health of reaction cells and pumps. They optimize performance based on electricity market conditions, weather forecasts, or grid demand. The system stores excess solar power during the day and releases it at night when demand rises. Integration with energy management platforms enables operators to make real-time adjustments. Digital coordination ensures the battery system runs efficiently and meets energy delivery targets without manual intervention. Pumps and fluid handling systems are central to the function of an iron flow battery. High-performance industrial pumps move electrolyte fluids from storage tanks to reaction cells and back. These pumps operate continuously and handle corrosive liquids without failure. Valves and sensors regulate flow rates and pressure to maintain system balance. Engineers design components for redundancy and long service life, using materials that resist corrosion and wear. Smooth fluid loop operation is essential for the battery to charge and discharge consistently and safely over time. Installation and maintenance of iron flow batteries are straightforward compared to other energy storage systems. The modular design allows easy transport and assembly. Electrolyte tanks, reaction cells, and pump systems install in standard shipping containers or custom enclosures near solar or wind farms. Routine maintenance involves checking fluid levels, inspecting pump performance, and verifying membrane integrity. With long lifespan and low wear, these systems require fewer interventions than lithium-based batteries. This reduces labor costs and minimizes system downtime, making iron flow batteries attractive for utility-scale deployments. Iron flow batteries could become part of decentralized energy ecosystems. Homes, businesses, and public facilities operate storage units connected to a shared smart grid. Local batteries communicate wirelessly to balance energy loads across neighborhoods, automatically shifting power where needed most. In rural or remote regions, small iron flow systems pair with solar or wind installations to provide continuous off-grid electricity. Future versions may incorporate self-cleaning membranes or automated fluid rebalancing systems, allowing operation for years with minimal maintenance or technical intervention. If current testing yields positive results, Australia may become one of the first nations to deploy iron flow batteries across entire regional grids. These batteries serve as long-term backup for solar farms, provide overnight storage for residential zones, and support isolated rural communities without relying on fossil fuel generators. In the future, mobile versions might be used during emergencies or large events to stabilize local demand. With long lifespan, fire resistance, and simple maintenance needs, iron flow batteries offer a dependable foundation for future energy systems. Thank you very much for watching. Please like and subscribe.